Chapter 6, number 38. Find the acceleration of the masses shown in the figure, given the masses values, and assume the table is frictionless and the masses move freely. Since they move freely, and since there's an unbalanced weight over here, it's going to descend, pulling the other guys over, so we really want to find their accelerations. Since they're connected by ideal strings, which cannot stretch or shrink, the distance along the string between this guy and this guy has to stay constant, and between this one and this one have to stay constant, which boils down to saying they must always have the same velocity, which in turn means if they always have the same velocity, then they must always have the same acceleration. So the trick to this problem is that there'll be three boxes, but they all have the same acceleration. So we draw free body diagrams, and we say box 1, and then box 2, and then box 3. And we'll give it a name. We'll say that box 1 moves over with acceleration A, which means box 2 moves over with acceleration A, which means box 3 moves downward with acceleration A. And then we start putting in the important forces. So here we'll have Fg, and counter to Fg will be some tension, which I'm going to call Ft. I'm going to call Ft-A because it's in sort of rope A. And we'll call this rope B. And then that's it, because that's the only things in contact with block 3. There's gravity, which I guess is not really in contact, but gravity always acts. And then there's the rope, and only things in contact or gravity can act on things in mechanics. All right, so we can see that the pulley takes FTA and redirects it. So block 2 is being pulled on by the rope A as well, and so there's an FTA pulling to the side. And then there's sort of an FTB pulling block 2 the other way. And you might wonder, not badly, what about, for instance, the fact that block 2 has some weight, which I'm going to call FG2. And it does, but of course, equivalently, there's also some normal force from the table, which I'm going to call FN2. And we know that those two are going to cancel out. So although I have them there, in the end, all they do is keep the block moving horizontally. They're not going to tell us anything about the acceleration. Likewise, on block 1, there'll be some force G1 pulling down and some force N1 pushing up. They're not going to be that interesting, but we will get FTB pulling the other way as rope B tries to shrink and it pulls at either end. So we get something along those lines. That allows us to sort of talk about the net forces on each of them. For instance, the net force on block 1 is just FTB. And here I am really just going to talk about the horizontal force on block 1 because we know the vertical forces are essentially just going to cancel out. We're just going to get FG1 minus FN1 equals 0, and that tells us really nothing. Likewise, the horizontal force on 2, we call these like X and X, is, and we look here and we say, well, there is an FTA and there is an FTB, but FTB points the other way from FTA, so I'm going to call that a minus sign to be consistent with the one before. It's not urgent that we do that, but they definitely have to have different signs since they point in different directions. And then lastly, there'll be an F3Y. There are no horizontal forces, so we don't have to worry about finding an FT3X. There are vertical forces, however, because there is FTA pulling up, and we have FG, and again, it's opposed to FTA, so it will pull down. And here I'm just sort of taking the semi-traditional X and Y axes like that. All of that was stuff from the diagrams. All right, from Newton's second law, we have that the sum of the forces on 1 in the x direction is m1 times the acceleration in the x direction, or just m1a. And likewise, f2x is m2 times the acceleration of block 2 in the x direction, but that's also just m2a. And then f3y is going to be m3 times a3. But here we need to be careful because a3 is not a, but minus a, because the block moves downward, which is opposed to our earlier stuff. So that's going to play an important role as we move on. So now what we're going to do is combine all of these with all of these. And to do that, I'll want some more room, so I'm going to start moving some stuff around. So let's move everything to a useful spot. And now we can combine those two sets of equations. Combining those equations, we get the three that are shown here. And then the next thing that we want to do is get them to be just one equation. And the way to do that is to add the first to the second and then subtract the third. So the best thing might be to negate the third equation and then add all three of them. So we put a minus sign here, and then minus a minus is plus, and minus a minus is plus. So we end up with those. And then we basically say we add the left side and we add the right side and see what comes out. Because when we do that, we can say that FTA minus FTA, right, because we're adding them, cancel. And FTB minus FTB cancel. In other words, all the internal forces cancel, and we're left with only M3G. And over here, when we add, we'd have M1A plus M2A plus M3A, and we could factor out the A, and we would end up with M1 plus M2 plus M3 all times A. And so the acceleration can be written, which is kind of interesting, as M3 over M1 plus M2 plus M3, all of that times G. So that we have this kind of weird thing where we have the mass that's free to move under gravity divided by the total mass of the system. After that, it really is just plugging in some numbers. So let's see if we can get some more room. And we get that A is M3, which is given as 3 kilograms, over 1 kilogram plus 2 kilogram plus 3 kilogram, because Walker's a little cute, and that's all times the free fall constant, which is 9.81 meters per second square, and this ends up being 3/6 times 9.81 meter per second square, which is 4.9 meters per second square, including sig figs. Notice we weren't asked for the tensions. They'd be easy to get at this point, but they turn out to be irrelevant to our final answer. We can arrange for them to not be here.